All right, good morning, everyone. So we're going to continue talking about digital modulation now. And on slide 10 here, I'm summarizing what we did in the last lecture. Okay, so at the top of slide 10, I'm showing you the block diagram of a basic digital communication system, right? So you have input, we have a set of bits here. Okay, so M is my input message, and it's going to come from a set. So it can be one of any. So I wrote B. Maybe it's fair to call it symbols, right? It could be bits as well, or pairs of bits. Okay, so we have in this instance K symbols that we want to transmit, and what the transmitter does. Right here, I'm modeling just the digital modulation part of it. The transmitter is going to map the information I want to send, the bit or the bit sequences, to a transmit waveform, right? S of t. All right, and then this signal is transmitted through a channel that potentially adds noise. So here I've shown an additive noise process, N of t. I've written it as AWGN. So maybe we take a moment to say what is AWGN here. So the A in AWGN is additive. Okay, this means that this noise term is added onto the signal. So the received signal R of t right here is S of t plus N of t. So that's the additive. The W stands for white. Okay, and here white has to do with the statistical properties of the noise, right? Essentially, white refers to the power spectral density of the noise process, and what white means is that the power spectral density is flat. It's constant over all frequencies, right? Do you remember what power spectral density is? Who remembers what is power spectral density? So this should have been covered in your signals and systems class. Can somebody give me an idea of maybe very intuitively what is power spectral density of a random process? So in class, I can just call on people. So I'm going to do that. I'm going to just go and call on somebody, okay? And I want you to try. Kai Hua, can you tell me? What is power spectral density?
It tells you how good is the power signal.
Okay, all right, yeah. I mean, I think you're on the right track. So Kelvin says the power of signal at different frequencies. Yeah, absolutely. So it's how is the power spread out over the different frequencies. Okay, and so either Kelvin or Kaihua, do you remember how to compute power spectral density of a random process? Now, we've already said when we have a deterministic signal, we can just take its Fourier transform, right? And so far, when we discussed AM and so on, we had these deterministic signals, and I basically just took the Fourier transform. When you have a random process, you cannot just take the Fourier transform. So what do? Does anybody remember? Kelvin or Kaihua? Shuni, maybe I ask you. Do you remember?
Okay, can you repeat the first part of the question?
Right. So we're talking about what is white, and I told you it's when the power spectral density is flat. Yeah. So what is power spectral density? So somebody said it's something to do with the power of the signal at different frequencies. So that's correct. How do we compute the power spectral density?
From what I remember in 2023,
Yeah.
you square the Fourier transform and then you integrate or something?
Yeah, so this is okay when you have a deterministic signal. Like if I give you a cosine or a sine. A random process is a little bit different. It's a more of a statistical or stochastic quantity. Okay, so what we do when we have a random process is we look at the autocorrelation function, and then we take the Fourier transform of that. So the power spectral density is actually the Fourier transform of the autocorrelation. So when the Fourier transform of something is constant, what was that something? Do you remember, Shinyi? If
If a
the
what is constant?
say it again.
If a what is constant?
If the Fourier transform of something is constant, what is that thing?
If it's a DC value in frequency, that means it's actually a Dirac in time.
Yeah.
An impulse.
Yeah, it's an impulse, correct. So since the power spectral density is the Fourier transform of the autocorrelation, when the power spectral density is flat, it means the autocorrelation is a delta function or impulse. And if the autocorrelation is an impulse, what does that tell you about the process? It means that it's uncorrelated in time, that the samples are independent. Right?
Okay.
And that's good because that's a good property of noise. There's no reason why noise from sample to sample should be correlated. Okay, so again, getting back to we're talking about white here. Okay, and so white means your power spectral density is flat, or in other words, your noise samples are independent from sample to sample. Okay, the next part of AWGN is Gaussian. Oh, this is horrible. My Apple Pencil seems to be not acting in the best that I've seen it. Okay, so the G in AWGN is Gaussian. And what this means that if you look at the underlying distribution from which the samples are drawn, it's a Gaussian distribution. It's a normal distribution. And this is a good model for many engineering systems. I think I mentioned this in class, that we often model noise in engineering systems as Gaussian. And this is primarily due to something called the central limit theorem. Right? The central limit theorem says that when you add up a whole bunch of Gaussian, identical but independent random variables, that the distribution of the sum approaches a Gaussian random variable. Okay, so often when you don't know what noise is, and for example, in communication systems, your noise can come from other communication systems. For example, you know that if I'm looking at Wi-Fi, things like Bluetooth are interference. Even your microwave is operating in the same band as Wi-Fi. So if somehow your microwave signal, the signal inside your microwave, the microwave is the appliance in your kitchen that you use to heat up things, right? If somehow some of that signal is leaking out, it's going to interfere, right? So there's a lot of different things that can add up. You have lightning, maybe the ambient universal background, radiation, if it's strong enough. All that stuff adds up, and we model it as Gaussian. Okay, and then of course the last term in AWGN is just noise, which means that this thing N of T is undesired signal. It's noise. Okay, so we are looking at this model of a sort of, a very high level model of a generic digital communication system. So the transmitter takes bits in, or sequences of bits in, maps it to a transmit waveform S of T, which goes through a channel, which adds noise. Here, noise is an additive white Gaussian noise process, N of T, and you're going to receive R of T, and R of T is just a sum of S of T and N of T, and it's the receiver's job. The receiver, which has to do demodulation, it's the receiver's job to map the R of T back to the bits or sequence of bits that was transmitted. And the input message we call M, the estimate at the receiver is called M hat. So that little symbol on top of the M is like a hat. So when we write it, or when we say it, we say m hat. Okay, because it's an estimate of m. Because you could be wrong. Hopefully you're right, and m hat equals m, but you could be wrong. Okay, so it's an estimate. And my transmit waveform S of t, which is the output of the transmitter, comes from some set S, right? Uppercase S or script S, and script S is a set of waveforms, S1 of t up to Sm of t, right? And these things are defined in some symbol intervals a t. So t is the duration of the symbol interval. Okay, and this, of course, this will determine my bandwidth. Okay, so are we clear on this model? So this is the model that we've been talking about of a sort of simple communication system. Okay, so what we talked about last week in this context was we have this set of transmit waveforms, right, S1 through Sm of t, and we talked about representing the set of transmit waveforms in terms of a basis set, and that was called signal space representation. And so a basis set is a set of orthonormal functions, so they're orthogonal and have unit energy. Okay, so orthonormal is defined here. Okay, so we are going to define our transmit waveforms as linear combinations of the basis set, right? And so that's shown right here. Okay, so Si is a linear combination of my basis functions, and then there's a multiplying factor in front, Sij, which is just the projection. So Sij is just a projection of Si onto, right? So Sij is the projection of the ith transmit waveform onto the jth basis function. And that becomes the coefficient or the coordinate, right? So these basis functions actually give you a coordinate system. And the Sij is the value of the coordinate for the jth coordinate of Si. Okay, and by making this association, we can represent Si of t, which is a signal in time. We can represent it by a vector of length n. If I have n basis functions, I have a vector of length n to represent the ith transmit waveform. And this is a vector of length n. So it sits in Rn. The elements are real numbers. Okay, and we called last time when we plot Si on a on a coordinate axis, right? We call it a constellation point, and the sequence of all constellation points was called the constellation diagram. Okay, so this is where we ended last time, and I gave you a few examples. All right, since we're going to be talking about n-dimensional Euclidean space, so Rn is my notation for n-dimensional Euclidean space. This means it's vectors of real numbers of length n, and the length of a vector is the usual, square root of sum of all of the coordinates squared. We call this the norm of the vector, and we'll denote it by this. And in a similar way to the length of a vector, which is just the distance of the vector from 0, we can define the distance between two vectors. We just take the difference between their coordinates, again, and square it, take the sum, take the square root. Okay, and this will be our notation for the distance between two vectors, right? This notation is useful because, as I mentioned, the benefit of signal space analysis is this geometric view, and we're going to view the transmit signals as points in n-dimensional space, and we're going to manipulate things purely in n-dimensional space, and this is going to simplify significantly our understanding of the communication system, how to design transmit signals, as well as how to demodulate a specific digital modulation scheme. Okay, so this was kind of a review of what we did last time. On one page, we have the entire sort of explanation of signal space. So if you get confused, you can come back to this slide, and this slide should tell you about what is signal space representation. Let me, I'm gonna take a picture of this. Oh, whoops. Okay. Okay, so let's go on now. Yeah, so here I'm, again, just drawing out the 2D analogy. So if you look at slide 11 here, I'm drawing the 2D plane. So we have the two axes. Here's the y-axis, and here's the x-axis, right? So the x-axis and the y-axis. And, you know, if I have a unit vector, right? So let's call this unit vector, this phi1 is a unit vector in the y-axis, and call phi2 a unit vector in the x-axis. Actually, I think I meant to maybe make that, oh yeah. So this is the unit vector sorry, yeah. So these two are phi1 and phi2. Okay, so phi1 is there and phi2 is that, right? Now if I take an arbitrary point AB, right? So let's say this is some arbitrary point AB. We see that we can write any arbitrary point in the plane as a linear combination of phi1 and phi2. In this instance, it's just A phi2, right? Because I go A in this direction, you know, A in the x direction, and I go B in the y direction. Okay, and so this is the sort of linear combination, how you can represent a signal in terms of its basis functions. And then projection is basically, I'm going to take this vector S1 and I'm going to project it onto the Y. Okay, so I'm going to project it onto this. So I get this vector. So this long vector in the Y direction that has length B is the projection of S1 onto phi1. Okay, and we can see that, right? That's the coordinate. So the projection of S1 onto phi1 is that multiplying factor in front. Okay, so this, if you ever get confused about signal space, you can just kind of refer to the usual 2D and 3D analogies, right? All we are doing in signal space representation is we are extending that idea to function space here, right? So right, but in the end of the day, we're converting everything to vectors, right? So it's nice. This model here is actually going to be very useful because we are converting our function space into something like vectors in 2D or 3D or n-dimensional plane. All right, let's move on. So maybe I'll, this is an example that I didn't do last time. Last time I did BPSK, we did linear baseband. Let me do another example, okay? So I think that could be helpful to understand what's going on. So we're gonna look at 4PSK, which is also called QPSK, quadrature phase shift keying. So 4PSK means that I have 4 phases. So I'm gonna have 4 transmit waveforms. And I'm going to be a little bit clever here and write that. Okay, so here are the in this form here, where what's changing here. So I have a cos. So again, I'm modulating a carrier. So I have cos 2 pi FCT, but I'm going to change the phase of the cosine here. I'm going to change the phase, right? And this phase will go through 4 values. So n is 1, 2, 3, 4, and there's an n here. Right, so we can see that the 4 phases, if I plug in n into sort of 2n minus 1 times pi by 4, the 2 phases are pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. And because I have 4 transmit waveforms, I can get 2 bits per symbol. All right, now this is still, this constellation is still in the plane. So even though I have 4 transmit signals, I only have 2 basis sets, right? Essentially, you remember last time when we talked about linear passband, we said that at a given frequency f, there are only really two orthogonal dimensions, right? Sine and cosine, right? So sine and cosine here are my basis functions. So phi1 is going to be cos 2 pi FCT, phi2 is sine 2 pi FCT. The multiplying factor here in front is there to make the to give them unit energy. Okay, if you take this thing and you integrate and you square it, you'll get some factor there, all right? Essentially you get like t by 2, and this will cancel this. Okay, now in signal space we can write these 4 points as shown. So in signal space we get 4 points, and we can plot them as shown in the signal constellation diagram here. So there are 4 points here: S1, S2, S3, and S4. And if you remember, we have to do a bit mapping, right? We have to map. So here there's 2 bits per symbol. So I need to take sequences of 2 bits and map them to these 4 symbols here. And here I've used something called the gray code, which says that there should only be a 1-bit difference. Okay, so this gray code, there should be a 1-bit difference between adjacent symbols. So if you look at S1 and S2, you see that they differ in only 1 bit, right? There's S1 is 1, 1, S2 is 0, 1, and we see that they only differ in 1 bit. The idea there is that if you make a mistake, because we'll see that noise can push these symbols around, so it's more likely you're going to make an error to an adjacent bit. So if you make an error to an adjacent bit, like you transmitted S1, but you decode to S0, at the bit level, you only made 1 error. So that's good, right? If instead, if S2 was 0, 0 and S1 was 1, 1, you would actually make 2 errors. Okay, so that's the idea behind the gray code. Okay, so this is an example of QPSK, and I'm going to give you one more example of QAM. And I actually talked about 16 QAM before. So in 16 QAM, you have 16 constellation symbols, which means you've got 4 bits per symbol. And here I'm drawing out in the diagram here, I'm drawing out the 16 symbols here. Okay, there's 4 in each quadrant. And I'll just point out that information is being encoded both in amplitude and phase. Okay, these two symbols here are at the same phase but different amplitude. Okay, these 2 symbols here are same amplitude but different phase. Okay, so we can see that this geometric view is nice. It lets us visualize things quite nicely. Okay, let me. Okay. Okay, so let's talk about receiver design for the digital demodulation schemes. Okay, so to be able to talk about demodulation, we need a sort of a performance metric. The performance metric we're going to use is probability of error. Okay, and so I define PE here. Okay, so PE, so my notation for probability of error will be PE, and the goal will be to minimize the probability of error. Okay, I want to minimize PE. That seems like a good goal, right? I have a communication system where we're transmitting bits through these waveforms. We receive a noisy version of the waveform. We have to recover the bits. And my goal in designing how to recover the bits, I'm going to try to minimize the probability of error. Now, there's a fundamental issue, noise, right? When noise is added there, it's unlikely that I'm going to be able to decode all of my bits correctly, right? If you could decode all of your bits correctly, then you just do that, right? Your probability of error is 0. But noise is fundamental. It's out of your control. It's added by the universe. You cannot control it, and you don't know the noise. So the idea is that in the presence of noise, how am I going to minimize the probability of error? Now, a PE is defined here. Okay, so let's break down this definition here. The first thing is, let's look at this term here. This is the probability that that given that I sent MI is a particular message. So given I sent MI, what's the probability that my decoded message M hat is not equal to MI? Okay, and I'm gonna multiply that. So this is conditioned on MI being sent. Then I multiply it by the probability of MI being sent. Okay, then this right here is just a joint distribution that right? So this thing now is just the joint distribution of probability that mi is sent and m hat is not equal to mi, right? And then I'm going to sum this over all messages I. So is this clear? So this is just total probability. Is everybody okay with this? So I need you to understand this, because at the end of the day, this is the metric for decoding. We're going to minimize the probability of error. Can I get indication from you if you're with me on probability of error? By the show of hands. Okay, if you have a question on this, now is the time to ask. Either put it in the chat window or just, you know, unmute yourself and ask me. Okay, thank you everyone. Okay, good. So I'm going to move on. So before we actually do the receiver design, let's agree on a system model. Okay, so my system model, whoops. Can I erase that? Okay. Let's agree on a system model here. Okay, so my system model, okay, is here. Okay, so I'm going to have a transmit signal S of t. I'm going to have a noise process N of t. And my receive signal is going to be S of t plus N of t. Okay, so it's a very simple additive white Gaussian noise channel, right? I'm going to assume that N of t is a Gaussian noise process. I'm going to assume it's white. I'm going to actually assume that this is additive white Gaussian noise. Okay, I'm going to assume it has a flat power spectral density of N0 by 2. Okay, I told you it's flat here. I'm now just giving it a name. Okay, it's the N0 by 2 is there because I don't want to carry the 2 later. Okay, so now I have, for my transmit signal, I'm going to assume that the transmit power is PR. My transmit, X of t is my receive signal, sorry, not my transmit signal. X of t is my receive signal. I'm going to assume that the power I receive it is at PR. I'm going to assume that my transmit signal, S of t, has bandwidth 2B, and my noise has noise power. Well, since the transmit signal has transmit signal has bandwidth 2B, I'm going to filter it. My receiver is going to filter. So even though the noise is flat across all frequencies, the only thing that affects me is in my bandwidth of interest, which is a bandwidth 2B. So since this was the power spectral density, the power in the signal is just N0 by 2 multiplied by the bandwidth of interest. So my noise power is just N0B. And that motivates me to define the signal to noise ratio at the receiver as PR, which is the signal power received over the noise power. Okay, and we're going to see that the performance, the probability of error, is going to be a function of the signal to noise ratio, right? The higher my signal to noise ratio, the easier I can decode my signal, demodulate my signal. The lower the signal to noise ratio, the harder it is going to be for me to demodulate my signal. I think that makes sense to everybody, right? Okay, so again, this is just, we're sort of just defining the system model. It's going to be useful for us to look at things at a symbol and a bit interval. So ES is energy per symbol, EB is energy per bit. Then we have a symbol interval and a bit interval. Okay, the reason we have to do this is that symbols and bits are different, right? Remember, when we did 4 PSK, we took 2 bits and called them one symbol, right? So bits and symbols are different. They are not the same. Okay, so the signal to noise ratio, which was defined as PR over N0B, I can write it in terms of either symbols or bits. So when I look at it as symbols and bits, we get here. So as a function of the symbol quantity, it's just ES over TS N0B. And again, this is just a signal. So because remember, power is energy per unit time. So ES was the energy per symbol. So the power is energy per ES per the symbol interval TS. So this is the signal power. And we already know that the noise power was N0B. Okay, and then the same thing for the bit. Okay, we are going to sometimes define these quantities. So this ES over N0, so ES over N0 is going to be useful to call it the SNR per symbol, and right. So we get something called gamma S. So this funky symbol here is gamma, the Greek letter gamma. Okay, so this is gamma S and gamma B are the SNR per symbol and SNR per bit, and then we can talk about symbol error, probability of symbol error, and we can talk about probability of bit error. Okay, so right. So I defined this general notion of probability of error, but we can, when we think of symbols and bits, we can think of symbol error and bit error. Okay, so everybody good? We're going to see that the performance of our system, when we try to minimize the probability of error, is going to be a function of all of these quantities here. Okay, so on one page, we've defined our system model. So everybody good? Can I get a, so how about when I ask, everybody good? You let me know by show of hands, or you ask me your question. Okay, let me take a picture. Okay. All right, let's start now really looking at the power of the geometric approach. Okay, we're going to now start to talk about demodulation. So on slide 14 here, we're going to start talking about demodulation, and we're going to ask the question, what affects error performance? Okay, and we're going to really build this up in a very intuitive way. All right, I'm not a fan of formulas and stuff, right? So we're going to build this then up in a very intuitive way. All right, so let's take a very simple example. The example is going to be binary phase shift keying here, BPSK. Now, you remember for BPSK, the signal constellation is given by these 2 points, right? Right, so BPSK is a one-dimensional constellation. There are 2 constellation points, meaning the binary, right? And bit 0 maps to one of the constellation points, bit 1 maps to the other constellation point. So these are the 2 constellation points. And again, they have a specific distance from the origin, right? I'm going to call that distance A. And actually, when I wrote out BPSK, we said it's square root of EB, right? And that's because I want to say that this is the energy per bit. Okay? So, but for the moment, let's just call it A. Okay, so this distance from the origin of the point, the positive point is A, the negative point is minus A. All right, now when we transmit, okay, we are going to add noise, right? We said, right, my received signal is a transmit signal plus noise. Now in the time domain, I could write it, right? X of t is S of t plus N of t. That's what I said is the system model. But if we can actually go and analyze the time domain signals. But if you try to do that, it's possible. It's not really very hard. It's just very messy. But I'm going to show you how we can do it here. Now, we can, just like we can represent signals in signal space, we can represent noise in signal space. Okay? And so a noise is just a random vector. So in this case, it's a random vector in two-dimensional space. Now, I'm going to, so even though BPSK is a one-dimensional constellation, right? I told you that at a given frequency, there are actually 2 orthogonal dimensions. So actually your noise can be in both dimensions. Okay, so what's going to happen is if I transmit, so let's say I transmit minus A, right? In signal space, what's going to happen is my constellation point is going to get pushed around. Okay, so instead of receiving minus A, right, the original point, I'm going to receive something else, which I am kind of drawing here. Okay, right here. I'm going to receive that, right? So this is sort of my noisy received symbol. Okay. Now, if let's say, so let's talk about this. If I transmit minus a, if I, so let's give these things names. So I'm going to call this constellation point S1 and this constellation point S2. Okay. So let's say I transmit S2 and I'm going to receive, let's call this noisy receive symbol, I'm calling it X, right? So let's call this X1, okay? So let's say I send S2, but I receive X1. Now I could have sent S1 or S2, right? Are you guys with me? I really need feedback from you here because I'm making a logical argument. Okay, so I could have sent S1 or S2, right? Suppose I've sent S2 and I receive X1. Just based on complete common sense and logic, what are you going to decode X1 to? Are you going to say you sent S2 or S1?
S2.
S2.
Yeah, so people are saying S2. Can I ask why?
Closer to the S2 point.
Exactly. X1 is closer to S2 than it is to S1. So if noise pushes you around, it looks like choosing the closest point is good, right? It seems like it's a very natural thing to do. And it turns out that that's optimal. That's the beauty. That's the beauty of this is that demodulation scheme is the best thing that you can do. You choose the close, with additive white Gaussian noise, you choose the closest constellation point. Okay. Now, suppose that, so let's take another scenario. Suppose that I sent S2, but instead of receiving X1, I now receive, and let's call this a new point, X2. This is also possible, right? Because noise can push me around anywhere. So what would you decode X2 to be? If I receive X2, what would you say was sent? S2 or S1?
S1.
Yeah, because yes, the answer is you would, the nearest kind of the decoding scheme that I mentioned is called nearest neighbor decoding. The nearest neighbor decoding scheme would decode to S1. And that's, as I said, that's the best thing you can do. But in this case, would you be right or would you be wrong? So would you be right or would you be wrong by decoding to S1? Yes, you would be wrong. So Benjamin, you're right. You would be wrong because you actually sent S2, but there was a lot of noise and the noise pushed you past sort of the 0 point, right? So in this instance, all you need to do is to look at the X coordinate. If the X coordinate is positive, you decode to S1. If the X coordinate is negative, you decode to S2, right? That's this threshold decoding rule is just nearest neighbor decoding. But here the noise was too much. It pushed your your X coordinate over the 0 line, and you made a mistake. So can you see on here, if you could somehow change some property of the constellation, what property would you change to decrease your probability of error? Suppose you wanted it to make errors happen less often. What could you do?
The distance between the 2 points.
That's right, the distance between the 2 points. If you increase A, then the 2 points move farther apart. And in this instance, if I move them farther apart, that same noise that shifted S2 to X2, if A was bigger, that same noise wouldn't push you past 0, right? So we see that in the simple example, the error performance depends on the distance between the constellation points, right? So in this instance, the distance is just 2a, right? Because S1 is at A, S2 is at minus A. The distance between them is 2a. And we see that as A increases, error will decrease. And as A decreases, the error will increase. Okay? So this is the first thing I want you to see. Okay? And in fact, if you can understand this, you actually understand almost all of demodulation. Okay? What we're going to do now is we're going to try to make it a little bit more precise. Okay? Suppose I sent S1. Now, S1 is at A, and suppose that I get additive white Gaussian noise. So now, even though S1 is not random, my noise is random, and the noise has a PDF, right? So my PDF of my noise looks like this, right? What I've drawn here, right? So this is Gaussian noise, right? So this is the PDF of my noise. Okay, so this is meant to be my version of a normal distribution. Okay, so this is the PDF of the noise. If I add this to S1, what is the conditional PDF of the received signal given S1 was sent? It's just the PDF of the noise shifted to S1, right? So I have A here. Okay, this is A, and the PDF of the received signal, if point A was sent, if S1 was sent, is just the PDF of the noise, right? Shifted to S1, shifted to A. So are you with me on that or not? Is that good? It shifted because, so remember, X of t is S1 of t plus noise, right? So, and I'm looking at the PDF of X of t, right? This is the received signal. So this thing has the Gaussian PDF, but this thing is at A. So the PDF of the received signal, if S1 was sent, is just given by this. Does that answer your question, Jihao? Give me a second. So Ivan, you just asked me a question. The answer is no. Everything is fine. Okay, I mean everything is good. There's no problem. Okay, so in fact, we are not so far from being done here. Okay, so if you look at so this is the PDF. This is the PDF. In fact, can I change color? I think I can. I can figure out how to change color. Okay, never mind. Is it here? No. Okay. Yeah. So this is the PDF of the received signal. Now, when do I make an error? I make an error when noise. So if I send S1, I get an error when noise pushes me from here to the other side, right? When it pushes me past the 0 point. If I send A, and this is the PDF of the noise, when the noise, when the received signal is on this side here, then I'm going to make an error, right? So if this is the PDF of the received signal, what's the probability of error? It's when the noise is here, and it's just the area under this part of the curve. So the probability of error is just the area under the tail of the Gaussian, the shaded part. Is everybody with me? So when we have Gaussian noise, the analysis is quite straightforward. And we saw that we can, at least for BPSK, all we have to look at is the Gaussian distribution and find the area under the tail of the Gaussian. Now, for those of you who may have seen this before, this is something called, there's something called the Q function that captures the area under the tail of the Gaussian. Okay, so I think what I'm going to do is I'm going to stop here, okay, because I think there's an important conceptual idea here. Okay, that important idea is that the signal space representation allows me to look at the analysis of the communication system from a visual point of view, right? And you combine that with your knowledge, some knowledge of probability, we can actually get a very good idea of sort of the error performance, right? And even from the graphical view, you're even able to kind of deduce what is the optimum receiver, right? It's the nearest neighbor algorithm, okay? So in this very simple example, we actually closed the whole loop. We figured out, given this constellation, how to make the error performance better, right? How to decode it optimally, and how to even get a quantitative handle on the error performance. It's just the area under the tail of the Gaussian of the shaded part in the curve that I drew. All right, so somebody asked a question. So ideally you want the distribution on the side of S1 axis if you transmit S1 to have the best error performance. Yeah, but what we're actually, yeah, so so Benjamin, you are right. When I send S1, it's the shifted distribution to the right. If I send S2, right, the conditional PDF of the received signal condition on sending S2 is the Gaussian shifted to -a. So somebody was asking why is it shifted? Okay, it shifted because Pauline, you asked why is shifted. The received signal is just x of t, and x of t is S1 plus n of t, right? N of t has this PDF. Now S1 of t is not a is not a random variable. It's a constant. So it's like saying, and here S1 in signal space, if you will, in signal. So I'll put a equal sign here, like this, a tilde equal, because it's not in time domain, but in signal space, I'm just sending a plus some Gaussian random variable n. A, so this is if I'm sending S1, I'm sending a plus n. This is a Gaussian random variable. This is a constant. So what is the PDF of a Gaussian random variable plus a? It's just, so if this thing has 0 mean, what's the mean of a plus n? It's just a, right? That's why the PDF of this is just that, the shifted version of the Gaussian. Okay, and so Benjamin, to close the loop on what you asked, if I send -a, then I'm going to get the PDF here, right? And again, then the probability of error. Yeah, I really got to figure out how to change the change color. The probability of error is on this side. I won't color it. I'll just like lightly shade it. Okay, so that's the probability. The area under the tail on the right is the probability condition on sending -a. The area, the tail of the Gaussian on the left is the probability of error condition on sending +a. Now, what I have to do is I have to average those, right? I again use total probability, and that is right here, right? If you remember, here I do right. I sum of the probability of sending both of my symbols. So I'll have probability of sending a times the probability of making an error given a was sent, plus the probability of sending -a times the probability of making an error given -a was sent. Okay, Benjamin, does that answer your question? Okay, so I think let's end here. You try to understand at this point the value of the signal space representation. When we come back, we're going to try to make this a little bit more precise.